Hello? Perfect. Good evening, and thank you very much for joining our fourth backend meetup. This is a recurring technical event focused on technologies. We are going to have three amazing speakers talking about the work that they're doing here in HubSpot. Personally, I'm a developer here, and I use their technologies all the time, and it's just great when you can use technologies that simply work, and you don't have to worry about, oh, if I use this, will it actually work, or do I have to ask someone about it? So our speakers for this evening will be Paul Hemberger. He'll be talking about distributed versioning in distributed systems. Then our director of engineering, Kerry Munz, will tell you a little story about how we got from starting out as a small company and growing to a large company where we have dozens of thousands of customers using our systems in a reliable fashion every day. And then Michael O'Brien will take you through the story of how we built our own email sending system and what challenges they faced there. So without any further ado, I will be asking Paul to present for us.
Hi, everyone. Can you hear me all right? Cool. So my name is Paul. I'm a tech lead here at HubSpot. It's awesome to be able to talk with everyone here today. So thank you for having me. The topic that I wanted to cover today is versioning in distributed systems. And just as like a general preface, like we're not going to be like breaking ground on like any like revolutionary techniques in distributed systems, but I was interested in taking a relatively simple idea using version numbers, assigning version numbers to data, and showing how we've taken that idea and used it as the basis for a couple of different systems that we've built out, and it's really like helped solve some problems, and hopefully I can impart some knowledge there, and maybe it's just interesting to hear how we've tackled some of these. So I imagine many of us have written in like an application that looks a little like this. You have some service, it's absorbing HTTP requests, and you talk with one database, and like everything kind of makes sense. Like, is your data consistent? You just ask the database what the latest version is, and everything's relatively simple. And then a week later, you've got something that looks like this, where it's just like, oh man, we need caching, and we need all this other stuff that people keep asking for. And all of a sudden, the very simple application that you had that had a really simple data model of being like, oh, like, what's the state of the data? Just ask the database. It's like, well, now that data might live, it might have semi-stale versions in cache. You might have some of it living in a data warehouse. You might have all sorts of message queues, and the state of the data within your entire system becomes very murky. And that's not a very compelling story to tell customers who are looking at your application being like, why is my data inconsistent? Like, I updated on this page. How come it isn't reflected in this graph? Why isn't it over here? Being like, well, it's hard. And so it's like, how can we better reason about data within a very large, complicated system? And one of the tools that we found that's very, very helpful for this is really a very simple idea, which is assigning version numbers to the data that we're operating on. And so at the top here, imagine we have some table, we have an object, its ID is 1, the data is foo, and when we create it, we assign the version number v1, which makes sense, we just created it. Now, one of the key things here that I'm going to mention is like if we're building on top of a data store that has ACID guarantees to some degree. So if you're using MySQL, if you're using Postgres, you can have ACID guarantees like across a single row, across multiple rows, across tables. You can do some crazy stuff. And so your version numbers can be very complex based off of like many other rows. We use a lot of HBase, which gives you per row level ACID guarantees. But you want something like that. And then like the key point here is that anytime you manipulate your data, you also increment the version number. And if it's atomic and consistent, then we're going to wind up in a state where you, like every time you touch that data, you're also incrementing the version number. And this simple idea can be very powerful because it helps frame an application rather than just like a pile of immutable state, like what's the latest version of it is sort of unknown. We now have like pointers to different states of the data. We can be like, we're operating on the data at version 1. We're operating on version 2. And I think this can really help like tie together a system. A good version number should be pretty quick to generate that value. A lot of times it's just throwing an increment onto the existing value, and strictly increasing is very nice because it wouldn't make a lot of sense if you have data at version 3, you update it and you get version 3 out of it. Or if you have something decreasing, it could be quite complicated. So that's the building block for some context, like using version numbers. So let's dive into the first of two examples of where we've used version numbers within our systems. And the first is to achieve better eventual consistency in one of our systems within the HubSpot CRM. So this is powering sales and marketing customers. And eventual consistency in the context of a distributed system is sort of like asynchronous processing. It's like you tell the database, take this update, and the database says, sure, I'm going to do that. And it may or may not be reflected eventually, but over time it will converge to the correct value. So when we look at the HubSpot CRM, there's a lot of different usage patterns for the data that customers have. So they have contacts, and they have companies, and they have deals, and they really want to search over it. So something like ElasticSearch is a fantastic data store for it. We also want to be able to scan over that data and hit some data store really hard in order to generate analytics and all sorts of other things. And something like HBase is great. So it's like, do we have to choose just one of these? And the answer is no, we actually use both. And so we mirror our data sets between HBase and ElasticSearch in order to handle all of these different use cases. So reading from left to right, the general request cycle for like, how do you keep these two data stores in sync starts with an API, and it'll say like, all right, we're going to put for key X some value Y into HBase. Right after that happens, we write an update to a write behind log. It's a replicated log. It's stored in Kafka, saying this is the change that happened. Then we have a log worker tail that, and so it's consuming all of the events. So it's like all of these objects have changed. And so now it then goes to HBase and fetches the latest versions of those because it knows something has changed. So it fetches those records and then creates an index request and throws them into Elasticsearch. So in this situation, we're going to say that Elasticsearch is eventually consistent with respect to HBase. If the Kafka worker is keeping up, then Elasticsearch should reflect all of the same values that are in HBase, but it indexes them in a completely different manner. It exposes totally different access patterns, and this is awesome because now we can give customers reporting and search powered by Elasticsearch and still use HBase for a lot of other usage patterns. In the real world, it's a little more complicated. So when we're funneling data into Elasticsearch, Elasticsearch is eventually consistent. We're not updating Elasticsearch directly when, like, say, a contact record is updated. Then there can be many, many different services that are all writing to Elasticsearch at the same time. In addition, all of our messages to Elasticsearch are funneled through Kafka as well, and Kafka processing isn't guaranteed to be totally ordered either. So now we can wind up in a situation where multiple writers might be writing the same document to Elasticsearch at the same time, but they have different versions for it. So one has a stale, like some stale document, one is the fresh document. It's like, what order do they go in, and like what does Elasticsearch end up with? And it's sort of like last write wins, which isn't very satisfying. If like a customer is like, hey, how come my data isn't updated? It's like, well, I don't know, like it's hard. So then the solution that we've come up with is like, how can we use version numbers to make sure that Elasticsearch is going to be at least like, it's still going to be eventually consistent, but how can we make sure that we're always progressing forward? We can never regress in the version that Elasticsearch is showing. So to do this, we assign version numbers to all of the objects that are stored in HBase. And we have an HBase coprocessor, and a coprocessor for HBase is a little like a stored procedure for something like MySQL. And so any mutation that comes in that our client sends to HBase, the HBase coprocessor runs on the HBase region server node. So the clients don't actually have to know anything about version numbers. And so now the HBase coprocessor takes every mutation that happens and appends an increment to the version column that lives on that row. And because HBase can give us asset guarantees over a single row, we know that we cannot make a mutation to a row in HBase without also incrementing that version number. So the version number is in lockstep with every update to that table. So that's very cool. So then the next question is like, all right, we're versioning our objects. Like, what next? Like, how do we make Elasticsearch respect that? And Elasticsearch has an awesome external versioning system. So it can respect the version numbers of the documents that are passed in. And so you can just say like, Elasticsearch has 2 documents, 1 and 2. They're at versions 11 and 1. And so if we send it a request saying like, only version this if it's greater than the existing document, it will allow that, being like, sure, you're passing me a document that is more recent than the one that I know about. And on the flip side, if we pass a stale document, something like Kafka played out of order, or multiple writers were competing and something has stale data, it will reject documents that are stale. So now we can complete the picture by pulling that idea into this diagram. And so we can say, this is the real system. We have a version coprocessor which is running on the HBase region server nodes. We never have to think about version numbers when we're making changes to HBase. And then the log worker, when it's fetching those, when it's tailing that log saying, oh, object X has changed, I'm going to go fetch the latest version of it. It will grab the version number and pass that along into the Elasticsearch index, and Elasticsearch will be like more correctly eventually consistent. And the total lag time for the system is typically like sub-second between a write to HBase and the update being reflected in Elasticsearch. And so this is a system that has worked out really well for us. And in one case where like version numbers have really simplified a tricky problem. The next chapter is around caching, which is always like a very challenging topic. And a lot of times when you're throwing a cache into an application, it's for performance reasons. And if your application can tolerate stale data, then like you're kind of home free, like caching is awesome. If your application can't tolerate stale data, but you still need a cache, that's when things get a little tricky. And the scenarios for us is that there's certain types of access patterns that are really, really bad for our downstream data stores like MySQL. And so we want to avoid hotspotting. We want to like increase the availability of the threads on the MySQL boxes. And like the way we are handling MySQL, it's like we can really only scale like so far so easily. And so we want to throw a caching layer in front of that. But because we're using a caching layer in lieu of MySQL, we also need it to be correct. Like we cannot tolerate stale data. So I'm going to define cache correctness for the purpose of the talk. This is not a real term, as saying that the cache never returns stale data. So it's like if you ask the cache, you ask the database at the exact same time, they return the exact same result. A very common pattern for interacting with a cache in an application is going to be something like this. You write a change to your persisted data store, MySQL, HBase, what have you. Then you go to your cache and invalidate it, saying like those values are like they're inaccurate, and it forces readers on the next time that they're accessing that value to go fetch it from the canonical data storage. So then the question is like, can the system return stale data? I can't answer that with more questions, which is like, have you considered these cases? And my general thinking around this is like, there's really no way to avoid some possibility of stale reads if you're like following a pattern like this. And so if we're thinking about cache correctness, is like, this is kind of an incorrect design. It might be correct like almost every single time, but like with enough traffic, like those ones where it's not right are going to be a challenge. So how do we think about caching in a way where we do not return incorrect data? And this goes back to version numbers. And when I was saying before, it's like versioning is really nice because you assign a number, you assign a pointer to a particular state of data. We can do that as well for the cache keys. So rather than having some cache key try to point to some data and you try to keep that data in sync with your data store, what if every time your data updated, you got a new pointer? So that's this idea. Probably best illustrated with a diagram. And so reading time from left to right, we have some service that's trying to get values for key X. The service begins by asking your underlying data store, give me the latest version for key X. It's not asking, give me the latest value, just give me the latest version for it. And so in this case, say a MySQL box will return you, say key X is at version 1. So now the service can concatenate your key with your version number and ask your cache, in this case memcache, it's like, give me X at version 1. And if the cache has it, then you have the correct value because you were told version 1 is the latest value for it. Things get really interesting on a cache miss. So now, say the service has just updated the data at key X, and it has evolved to Y prime at version 2. So now when somebody's trying to answer the question, what's the data at key X, you ask MySQL, give me the latest version for key X, and you get version 2. So now you can concatenate them together, and you get X at version 2, and you ask your cache, give me X at version 2, and what do we get? A cache miss. So we've created an implicit cache invalidation by assigning this version number to the cache key. We never had to say invalidate that value. by updating the value, by having the ACID guarantee that the version number is going to increment every time we touch that value, we have gotten a new cache key, and therefore we've created this cache miss. So now you can go to, in this case with a miss, you're like, well, now I need to get the real value. You can go to your backing store and then return y prime to your client, and then insert that value. Exit version 2 is y prime. And so that's the idea of generational caching, is like, this is a way to cache data that is going to be consistent, correct with respect to your backing store. And you never had to think about explicit invalidations, which is really, really nice. You might also be looking at this kind of cross-eyed, being like, but didn't you just like go to MySQL to ask the version number? Like, why didn't you just get the data from MySQL? Which is a totally valid question. And I think it really depends on the type of access pattern that you're looking to have with your cache, and like the type of data that you're storing. If y were a very small value, just return y, and just like don't bother with the cache at all. In the case for us, there's certain caches that we have where like a version number is like a long, and the value itself could be potentially like hundreds of kilobytes to low megabyte range, and that's going to be much more taxing on the MySQL server, especially dealing with like large bursts of traffic. So to walk through an example of one cache that we use, we run this query around 4,000 times per second. So it's saying select all list definitions where given, like there's a given portal ID. Not going to go into list definitions, but it's an object that our customers can create, and a portal ID is one customer. So we run this to the tune of 4,000 times per second. It's pretty frequent. And we want to be able to cache this value. So how do we assign a version number to a collection of objects? Because this is the collection of list definitions within a particular customer account. So we say select the max updated, last updated timestamp for any of those objects within their account. And say that's going to be our version number. So anytime somebody creates a new definition, somebody updates one, that max of last updated will also increment. The cache key then becomes the concatenation of the customer account that we're talking about and the last updated timestamp for this set of data. And then we actually couple that with internal cache. So it's like the host making this request to memcache also keep a local cache as well. And they can just share the same cache key. It's like versioned in the same way. So if you get the last updated timestamp, you ask, is it already on my box? If it's in memory, that's awesome. That's super fast. If not, populate it from memcache. If not, populate it from MySQL. So how well does this one work? Pretty well. I was like pretty like pumped putting together the numbers for this because I actually didn't know. So out of 4,000 requests per second, only 10 of them thereabout actually hit MySQL and grab list definitions from them. So the hit rates in the internal cache and on memcache are pretty high. Of course, you still had to go to MySQL around 4,000 times per second in order to grab those version numbers. So like, is it like, does that make sense? Is it worth it? And so I think it's worth looking at some like the worst case scenarios, which is like what we're really trying to avoid. Like these are the situations that produce a lot of instability with the data source that we're using. If we wanted to grab a really large payload, like all list definitions for one really large customer. So like HubSpot, the company runs on HubSpot, the product, and is a very large customer of the product. So if we're grabbing, that's sort of my like my pessimistic case is like trying to do this for HubSpot's account. If we try to fetch that whole payload from MySQL, the entire round trip time is 5 seconds, which is just awful. And for memcache, it's 1.5 seconds. And for a local cache, which is almost certainly going to be in, it's 150 milliseconds, which is like, that's like pretty good. And that includes the round trip time of having to go to MySQL first in order to fetch the version number. And so it's like we use a covering index on MySQL, so it never even has to go to the primary key. And like if this is hit frequently enough for large accounts, it'll probably just be like thrown into memory on the MySQL host itself. So the requests to MySQL are much, much faster than trying to return the whole payload. Some of the downsides is when you start thinking about caching, not just as like an optimization, but like something that you really need in order for your system to work, you really cannot tolerate any bugs. Like any like cache invalidation errors or like anything along those lines is now a real bug in your system rather than being like, oh, it's like slightly more stale than it used to be. So that's been a challenge for us, is just like really like working out all of the like the tricky bugs that come along the way. So we also have like a pretty strong dependency on memcache as well. So my takeaways here is just like I found versioning to be really helpful to like think about data as like moving through a series of states and just like help frame a system in more of like a state machine manner with like transformations between those states. And I think that's been really, really nice as we start to model some types of problems of being like, all right, we have a cache that can't return stale data. How do we think about that? How do we build a better pipeline between these two data stores? And if you're not like used to assigning versions to everything, I'd encourage you to take a look at these two queries at the bottom and kind of like squint at them and be like, what's the difference here? Because I think you'll find that the one on the right is really like much more well equipped to handle multiple writer situations and is a form of optimistic locking where it's like you don't update the data just blindly, you only update it if you think you have the latest version. So that's my, my blurb on versioning. Does anybody have any questions? Sorry? Yeah, Elasticsearch has a bunch of different versioning systems. So it can use an internal versioning system where each time it sees the same document over and over again, it just increments its own version. But you can also set it to respect an external versioning system, being like, just trust whatever version is thrown onto the document that it's given. And it can even be tuned where like it'll only accept versions that are greater than or equal to its current version or strictly greater than its current version. So Elasticsearch actually has like a lot of cool knobs to fiddle with there, depending on the usage.
One moment, please.
How do you scale the versioning server? So if the server goes down, so what happens? And like, do you have one instance of the server, or you have redundancy? Yep.
So we don't actually have a in like the examples here, we don't actually have like an explicit versioning server. So for instance, like with HBase, the coprocessor is just throwing increments onto existing mutations, and then when each of those mutations runs, it just does that for it. Somebody within the company did write their own versioning or like their own like monotonic, or I guess it's actually like strictly increasing system in terms of like, just give me an ID that's greater than the one that you gave me last time for a given namespace. And that one I know some people use for similar purposes. And I think it's just sort of like creates like a pool of possible next IDs. And when you request it, it gives you like a chunk of those. So it'd be like, all right, here's the next 50 that you as a client can use without having to like ask 50 times in a row.
Question: do you use versioning for all kind of data? Like, for example, I understand when you query by collection, so it's a huge payload, and you get the version, and it's faster to go in the cache. But if you do a lookup by ID to get the version, and you need a single value, why don't you get the single value in that moment?
It depends on the size of that value. In the case of like, say, these list definition objects, it wouldn't make a lot of sense if you were fetching a single one to be caching them on like an individual basis. It really only makes sense to cache them in aggregate, and because that like in aggregate, it's a relatively large payload. And when we're using them, you kind of need all of them. So that's a particular case where I think it makes more sense. Where it makes okay sense to use that type of versioning. If it's a single row, like if it's a small payload, it's just like, don't pay the round trip time twice.
So I don't know if this is a valid question, but when you're updating a document in Elasticsearch, do you just check if the version is bigger than the last one, or do you have to check if it's the next version? Because I'm thinking, for example, if it's on current version 1 and then version 3 comes along before version 2, do you get inconsistent data? Because if you're changing different parts of the document, what happens then?
So Elasticsearch doesn't allow partial updates to documents. So it's like it throws out the entire existing document and reindexes the whole thing. So if it went like 1, 3, 2, it would move from 1 to 3. And then when the second document is requested, it would say like, I already have 3. I'm not going to, or like when it gets 2, it's going to say, I already have 3. I'm not going to index that one.
Okay.
To what extent did you use the semantics of the web in order to, or did you consider using web semantics in order to specify object identity and object versioning, and then you could use, I guess, all the infrastructure of the web for your caching, etc.?
So we pass around versions like pretty much as much as possible to identify objects. Where if you're operating on like some version, like sometimes we have like background workers, like just make sure this is still the latest version, like as we're doing some flow on it. I had another idea, but now I can't remember it at the moment.
Yeah, I mean, a lot of this seems very familiar and relates to, I guess, the freshness of web pages and the identity of web pages themselves. And there's a lot of infrastructure that's already out there that does a lot of the caching and invalidation, et cetera, for you.
Yeah, I'm not as familiar with anything that would like kind of do this out of the box. So I'm happy to talk afterwards and hear about how we could be doing things more simply. I would just mention one last final thing: the taking document ID plus version as like identifying tuple for a particular state of data is very useful. And we've also found it super useful to be logging it everywhere, because then you always know it's like, oh, this operation worked on this specific like incarnation of this data. And that's been really, really helpful to look at in retrospect as well. Thank you, guys.
Okay, thank you very much, Paul. Remember, if you do have more questions or more in-depth questions, we will be around after the event as well. So next up is Kerry Munz, telling us about how we got HubSpot from a small company to a large company and how our infrastructure had to grow alongside it.
Thank you. Hi, so I'm visiting over from Cambridge, Massachusetts. My name is Kerry Munz, and I'm the Director of Engineering for the platform infrastructure teams. And exactly as we were told, we're going to be talking about, what are those key principles for HubSpot that we've used for scaling up our platform infrastructure. What are some of the tools that we use and some of the choices that we made, and then a few stories from our own journey. So this is the question we're going to answer here. How do you evolve your platform infrastructure from a startup? This is, an example of HubSpot running on Dharmesh's laptop. All the way to today, we're at 2.75 trillion HBase requests per day with 10,000 deploys per week. And multi-regional now, we're running HubSpot both in the USA and in the EU. And we recently just had a partnership with Google Cloud. And so we are now running across Amazon and Google Cloud. What are platform thinking principles? And really for HubSpot, this comes down to, 3 key things. One's a little, I think a little controversial for other companies, but it's about automation, usability, and reliability. So automation, this is about automate all the things. At HubSpot, we actually don't hire system administrators, and we don't hire people who are just strictly doing operations. We really hire engineers. Automation is really important in your platform infrastructure. And what we're talking about I should probably define it for everybody. Platform infrastructure is really the VMs that you're running in your cloud infrastructure. It's those servers that you're running all of your microservices on or your services on. It is also your networks. It is load balancing. It is all of your data infrastructure. So ElasticSearch, HBase, Kafka, Presto, you name it. It is also monitoring and metrics. But the biggest key part for HubSpot, where we give our goal is to give our engineers superpowers, is really our build, deploy, run, and debug workflow. We want to make that as easy as possible for our engineers. So automation in platform infrastructure is really important for consistency for servers. It's also if you have any failures, and failure is really the norm in platform infrastructure, you're going to have a slow MTTR, which is mean time to repair. It's also automation is really important because we don't want our engineers to be waking up in the middle of the night to do things that they can build systems to be doing for them. So again, automate all the things. Don't hesitate, automate. This is just a common thing. If we see somebody doing something more than twice or doing something manually, it's don't hesitate, automate. So part of our journey, this is many years ago, Puppet became a big part of that automation. And what Puppet does is it gives you consistent server configuration, and it allows you to configure servers as a simple configuration file that we keep in GitHub. It makes it so that we can reproduce any server if it fails. We can also scale up by reproducing that server just based off of the configuration file. It makes it very repeatable. Another big part of our automation journey was when we built Singularity. And so the way that we used to work was, today we have about 60 teams, and this is back when we had many dozens of teams, and they were all responsible, much more vertically organized, and they were responsible for their own EC2 instances. Our deploy system would just deploy directly to, everybody had access to the Amazon Web Console. They could spin up whatever size server that they wanted, and we were letting them use good judgment, which is, do it based off of the size of your service today, but everyone would just over provision and buy the most expensive box they could find. And we were wasting a huge amount of money that way. It was also a big pain in the ass for people because, they're maintaining their own servers. You want to be writing features for your customers, not just focusing on, is my server failing? Do I need to scale my system or not? So our team, brought in Mesos as a framework, and really Mesos is an Apache Mesos framework. It's about scalability, fault tolerance, resource isolation. It lets you run your microservices, your jobs, your tasks, all on a shared pool of resources. And we built Singularity on top of that as a way to be able to give our engineers a really easy interface. It does a lot of the scheduling itself, but it's also to give them an easy interface so they never have to log into a box. They have a tailor to be able to see, what are those log messages that are coming through. And this actually made a huge difference. It decreased our costs massively. We were able to decommission thousands of servers, but it also made it, suddenly writing a service at HubSpot was no longer a hellscape. It was just a very simple thing to do. So that led us to the second principle, which is usability. And we actually put a lot of calories into usability for our platform infrastructure. For hard to use tools means a slow development cycle. And just, if you think about that for HubSpot, we have approximately 400 engineers. And the way that we look at it on the platform infrastructure team is if we can save all those engineers 30 minutes a day so that they're not sitting and waiting for a build, or they're able to get information from their logs and debug problems in a much faster way, we're going to say we actually have this magical 24 extra engineers, in our pocket that I keep hiring them for the platform infrastructure team. So this is how I keep justifying our team growing, but it really is a massive force multiplier for HubSpot, and it makes our engineers' lives much easier. This is just one simple example. We actually use all of the same components. So all of our UI components are written in React, and we use the same components in our own internal tooling. So this is Orion, which is our deploy tool. And it makes it very simple. We've really streamlined that workflow, make sure that you can link to GitHub, link to Singularity. It gives you a really easy way to deploy to production, to QA, deploy to production. And we can make sure that people are, using good judgment. They're not deploying after hours. We give them a warning, but still let them do that. And I'll continue. And so along with that, reliability is the third piece of the platform thinking philosophy. So the big problem with running in the cloud, many thousands of servers, we actually, it's shocking, we get about a 3 to 5% failure rate for our servers in Amazon. And we consider a failure, even if the network's flapping, we just, we hate those kinds of servers. They're the worst. They're the zombie ones that cause all the problems in our lives. It's also reliability. You become very unreliable when you become very popular because you need to be able to scale automatically. So we want to make sure that we can handle this automatically. We actually, a few years ago, did have big problems with reliability. It wasn't one of those things that we were focused on as a scale up. It was really product market fit, features, going faster and faster. And so we declared something called Code Red, and came up with like a very consistent, blameless post-mortem process just to be able to continuously improve all of our platform tooling. We also really focus on open source because, at the root of it, your infrastructure is still based off of code. So Linux is code. You can go and patch that. Docker, it's code. You know, if it's open source, you can go and patch it, and then you can contribute it back up to the community, and we can all benefit from this. We also have put a lot of calories, and we're doing even more of that right now on monitoring, because what we find is if you can create automated jobs based off of, you know, certain thresholds, you know, again, you get more sleep at night because engineers aren't waking up to make a decision. Is there a problem? Is there not a problem? Do we need to scale automatically? So we're using a lot of monitoring for that. So as part of our code red, you know, we had a goal in the year to get to 4 nines reliability for HBase. What 4 nines means is that you can have approximately 4 minutes of downtime. Before that, we were not at 4 nines for HBase. And so Paul had to come up with very creative caching solutions and things like that to make sure that his systems were reliable themselves. One of the things that we did to be able to now have 100%, you know, reliable replacement of all of our HBase nodes when we have approximately 150 now failing every month. We have a system we call Adreet. What Adreet does is it just pays attention to metrics, uptime metrics and CPU metrics, and determines, you know, is anything amiss, like even slightly flaky? If it is, we just kill that thing. And then its friend, Tranquility. Tranquility was called Tranquility because it lets our engineers sleep at night. All it's doing is monitoring the size of a cluster. And so this is really great. You just say, I want 250 HBase nodes for our email cluster. If it's at 249, Tranquility notices and just automatically spins another one up. So this is kind of a word salad slide, but this is how we divide up our platform infrastructure services now, you know, that we're a scale up. Infrastructure orchestration and security is a big focus. You know, I won't read all of these for you, but platform as a service, it's that build, deploy, run, debug, monitoring. You know, we put a lot of investment there. We have specialized data infrastructure teams. They're really, you know, big data team, processing team, the search team. They make sure that all of this data infrastructure is really reliable for our teams so that they can focus on their features and not about, are these servers healthy? We also have the front end of the service team, and they are fantastic, you know, creating all these reusable components for us, and we are open sourcing that as well. So this is just, you know, a little bit of, it sounds like we're bragging, oh, we had this great plan to get to where we are now, to be able to scale. And it was, you know, no, this is reliable infrastructure comes from frustration, rage code sessions, copycat squatters, multi-day crit sits, and tangled dependencies. But from all of these, so really what I'm trying to emphasize is that, you know, great reliable infrastructure comes from a lot of learning, a lot of great tooling, and really from need. It's built off of need. But I have to say that, you know, since we have eliminated a lot of these problems, now we have scaled up to deliberate planning. And so one of the things the team presented to us was, hey, we need to go multi-regional, you know, to be able to support our European customers. And we had never taken that on in the past. And so this was very new for us. And one of the things that we were dreading the most is spinning up 400 SQL clusters in the EU, you know, to duplicate HubSpot. So luckily we had enough lead time and said, no, there is a better way to do this. And the team decided we want to come up with a MySQL as a service for all of our engineers to be able to really automate this, more self-service, just make it much easier. So, because SQL was one of those, it was really our last data store that got a lot of really good attention because it was fine, but it wasn't great. People would still have to open a Jira ticket to get a database, and that's just terrible. Again, automate all these things. So we took an adventure and started working with Vitesse. And Kubernetes, and we have discovered, so Vitesse allows us to horizontally scale SQL across many clusters. You know, it allows you to join across many clusters, shard across clusters in a really simple, easy way. And it's all managed inside of Kubernetes, which is a big orchestration system for containers. And yeah, we are loving it. So we are actually starting to move all of the rest of our data infrastructure into Kubernetes, because this also gives us that portability to be able to then move to Japan and move elsewhere in a very simple, straightforward way. So if you only remember 2 things about platform infrastructure philosophy, it's really don't hesitate and automate. And then secret productivity tool is usability. Like, do invest calories into your internal tooling. It makes a big difference in the love you get from your engineers. Thank you. Any questions? Sure. Yeah.
I need to ask, because you mentioned EU and American clusters and potential expansion to other regions. Are you currently supporting the failure of one region and cross-region calls, or is that something that's not supported right now?
So the way that we did this, we actually only spun up very critical collection services, because we needed to, you know, as HubSpot, it's microservices. Everything is so interconnected. What we really wanted to do was to dip our toe in, be able to improve the reliability and the performance for collection services in the EU, but we didn't actually have to move everything. So yeah, I went off on tangent. I don't think I actually answered your question.
So what would happen if the US cluster went down?
Yeah,
or the
so
EU
if a US
customers?
cluster goes down, then our collection services, they stay up. And really the way that our systems are designed is that if any clusters go down, we use Hystrix to be able to load balance. We have sane defaults built into the system so that our customers are still going to get service. So, you know, we've been very explicit about that. When we were doing our testing, we kept cutting the network, you know, 100% between the US and the EU. And that was a, you know, a super fun adventure for us, because we discovered dependencies on our deployer that suddenly our EU engineer, or no, our engineers in the US were saying, well, we can't even do anything. What are you doing? We had promised them there would be no effect to our tests, but there were effects. So yeah, if a cluster goes down, it still works. We actually use Kafka to be able to maintain that data, and then it gets pulled back to the US when it comes back online.
Thank you.
Yep.
You said that HubSpot automate everything, right?
So
yeah,
automate everything. Exactly.
So how HubSpot start to automate everything? I mean, terms like when they start and how they start planning, like how the workflow of the automate everything.
Yeah. So you mean like how did our engineers start leaning heavily into automation? You know, it really was. For the reproducibility, this is, you know, way back in HubSpot's time. I wasn't actually there at the time, but like bringing in Puppet made it very easy for us to be able to reproduce clusters or reproduce systems. And it was really just that philosophy. We used to have engineers that would be more system administrators and write tiny scripts and not, but it was when we started, you know, bringing in engineers who had a lot of background on building systems. You know, they were just very insistent. This is the right way to build, and you know that kind of infected all of us. And so now it's just a common principle that we use.
So you mentioned that you run on AWS and Google Cloud. Have you any plans to move to Azure? And
No.
follow-up a question, if not, fair enough. You said you do some testing by cutting the network. Have you thought about running Chaos Monkey in AWS?
Yeah, actually what we're doing instead of Chaos Monkey, so we've been doing a lot of Chaos. We don't use the Chaos Monkey. We actually wrote our own Chaos Monkey integrated into Kubernetes. What we are trying to do actually this quarter is to have like constant chaos in QA. And one way that one of our great engineers came up with is we're actually, you know, dipping our toe into Spot instances. And in AWS, Spot instances are servers that are ephemeral. They may be ripped out from under you, you know, at any moment, but they cost 70% less than normal pricing. And when you run a free product, like you need really thin cogs. And so we're really excited about Spot instances, just because they are a natural chaos monkey for us. So we are planning actually, during the first half of the year to run all of QA on chaos, on Spot instances. So it's going to be, a third. I know that I haven't warned these guys yet, but this is one of the plans. We're not going to do it to everybody at once. You have to make sure you're not disrupting the whole company at the same time. But, we've got a lot of friends around who are willing to let us, torture them. We do have some services that are more sensitive to being bounced. And so, we make sure we're not causing chaos there. But, this is the dream. It'll save us millions of dollars. So thank you.
Okay, and our last speaker for this evening, Michael O'Brien. He will be telling us about Franklin, and I hope he starts with an explanation of what Franklin is.
Cool. Hi, everybody. Yeah, so I'm going to talk about, so my name is Michael. I work on email here at HubSpot. And I'm going to talk about scaling Franklin, which is what we call some of our email sending infrastructure. So first of all, HubSpot really loves email. It's actually kind of a big deal. It's a big part of the product that we offer to our marketing customers. We send hundreds of millions of emails every single week. That's a mixture of marketing emails, also transactional emails like forgotten password requests and these kinds of things. We have thousands of active customers who are using the system every single day. And we devote a lot of effort to getting this right. So we have like 6 email teams. 3 of those are in Dublin. So we have marketing email publishing here in Dublin, and they design the system that allows marketers to create great marketing emails and send them to their customers. We have marketing email analytics, which allows our customers to see, how did this email perform? Did a lot of people open it? Did they click on it? What did they do next? And then we have email sending infrastructure, which is my team, and we deal with the kind of nuts and bolts and bits and bytes of sending emails over the network and managing all that data. So, you might think, like, what is actually so hard about email? Why do we need 6 teams to, like, send a few emails? And I ask myself the same question sometimes. You're probably thinking, I've sent some email before, right? I, like, get some library, I connect to some server, I, like, send the email, I'm done, right? It seems like an easy problem. And so, one of the things that actually makes email hard is that it's old, right? It's really, really old. It's like 36 years old. Whenever the first RFC was published, we had like David Hasselhoff on TV in America. We had Bosco on TV in Ireland. And, the top selling computer had 16K of RAM, right? It was conceived for a different age. And SMTP has changed a little bit, but it's still like this really old, outdated protocol. The kind of transcript that you can see there is, shows you the kind of chatty and very like text-heavy nature of sending an email, right? We have to do all these kind of back and forth between us and the remote server, and they send us something back. And in this case, you can see there are like some status codes, 250 and 354 and so on. But sometimes we just get a message in text that we have to parse, and it's hard to know what that email server was talking about. Now, since 1982, things haven't like totally stood still. So there have been some extra standards, so we can send encrypted emails now, which is great. There's things like 8-bit MIME and SMTP UTF-8, where we can actually send stuff, in languages other than English, which is kind of useful. And there's things like pipelining and chunking, which allow you to avoid a lot of that kind of back and forth chattiness, but only some servers support them. So, you still have to cope with a lot of different behaviors by a lot of different servers. And in some ways, it's like calling the world's least stable API, right? There's tens of thousands of different hosts that we contact every single day. They have radically different latency, radically different throughput. We're literally like in 1 second talking to Google and an entire data center full of, Gmail servers, and also to someone's, computer under their desk at the other side of the world. And our system needs to be able to, behave reliably with all of these very different kinds of systems. On top of that, there's a bunch of other kind of weird problems as well. So we've got authentication and reputation. Nobody trusts anyone in email, right? This is just the truth of it. So we have to sign messages with DKIM. We have to register our servers in DNS so people know that these servers are actually authorized to send these emails. DMARC ties these together. If we send bad email, or if some of our customers send email that isn't wanted, our IPs could get bad reputation or could get blacklisted. We have to take a lot of care over that. And also, email just doesn't always work on the first try. It's not like you just connect and then it's delivered. Sometimes we might get a message saying, oh, you've just got too many connections. Just try again later. Maybe a minute later, maybe like a day later. Some individual email address might just not be working at the moment. On top of that, we need to like receive emails back. So if an email bounces, we'll get another email back saying, you know, this is why, and so on. And on top of all this, you know, we have a lot of email to send. So we have to have really highly concurrent network traffic doing SMTP and also DNS. So, you know, it's why would we even bother building some of this software? Like, we should just let a third party do all of this for us. And actually, for years, that's exactly what we did. And we still have some great relationships with some third parties that send email for us. But, you know, what we figured out is that our customers are depending on us to help them grow their business, right? So one of our customers is launching, you know, a great new sale. They want to email all their, you know, very best customers to give them some advance notice that, you know, we're going to have these great offers on our website tomorrow. We need to make sure that email goes out. And if it doesn't, we can't say, oh, it's a third party's problem, or yeah, you know, things happen. So we want to really own this. We want to have redundancy as well. So, okay, if our third party has a problem, or if our internal system has a problem, we want to be able to route around that and still deliver those emails. And you know, another big part of this was we wanted to kind of be experts in email ourselves. We didn't want to just call up to someone and say, hey, there's something we didn't understand. You know, one example that came out of this is this standard SMTP UTF-8, which I think like came out a few years ago. Google had a big blog post and nobody supports it. And if you want to send an email to somebody with you know, non-English characters in their email address, you pretty much can't do that with third parties. But we built that system into that standard into our system, and so now we support that for our customers. So that was important to do. So yeah, this guy here, this is Benjamin Franklin, and he's the name for our MTA, Mail Transfer Agent. He was the first Postmaster General in the US. He did a bunch of other things as well. So he like introduced a postal service when having a regular monthly delivery was like really, you know, amazing in Canada at the time. So our MTA, as I said, it runs alongside the third-party MTAs. We're still using those as well. It takes a while to build this software and to have it work reliably. So like the very first commit was kind of around the summer of 2015. In 2016, we started to actually use it to send email. We were, first of all, sending just HubSpot's email. So as Paul was saying, we're like our own biggest customer, basically. So we started to send, you know, like 5% and then 10% throughout 2016 to make sure everything worked. And then in 2017, we really took off. So we started to divert traffic from the other MTAs into Franklin. And, you know, throughout 2017, we had more than 20x growth. So to give you some context, January 2017, we were sending several 100,000 emails every day. And now we're doing about 25 million quite regularly a day in Franklin. So how does it work? How do we build a system like this? So as Kerry was saying, we have this really awesome platform. We use mostly Java microservices. So that's the way Franklin works. It's built in Java microservices. We use Kafka for our sending pipeline. If you haven't used Kafka before, you should. It's really high volume, really fast way of sending messages from one host to another. We use HBase for metadata. We also use it for locking. So Kafka is like at least once delivery. So you might get messages more than once. So we need to make sure we don't send emails more than once. We use HBase for locking to avoid that. We use Hadoop as well for MapReduce jobs. And we also built our own SMTP client because there wasn't a really great high performance one out there, and you can download that. It's open source. So, you know, like you might think, okay, had a certain level of traffic January 2017. We needed to scale that 20x, which is quite a big number. How do we do that? And so, you know, in some way, it was like, okay, we have a great platform. We have this singularity thing. We can literally click this button and, you know, go from like 1 server to 20. It's actually very easy to do. It turns out, right, the problem is a little bit harder than that, unfortunately. And, you know, one of the main reasons for that is that if you're sending a ton of stuff, or you're just handling a lot of volume, solving the same problem a bunch of times, even a tiny, tiny bug is really serious. So if we have something that affects, you know, 0.01% of emails, that's still thousands and thousands of emails every day for us. And so really the question was, you know, when we scale, what we want to do is we want to just find those bugs faster, right? Like those bugs exist. So what we want to do is to make sure we still have a reliable system at the end of the year. Like, how are we going to catch those bugs before our customers do? So we use some standard approaches. We use feature switches for everything. And not just like on-off feature switches, but, you know, let's send like 1% of our traffic through this new code path, gather some data for a while. If something goes wrong, we can quickly roll back, fix the bug, and re-release. Being able to iterate that fast means we need to be able to deploy several times a day. Again, we're, you know, relying on this really great platform that we can use to do that. We also built a big load testing system as well. So we want to be able to say, okay, let's send 1,000 emails a second. Let's send 5,000 emails a second, and let's see what happens. Let's really, really try and like kill our system the best we can. And we managed to as well, actually. You know, one of the things that doesn't seem like a technical solution, but was actually hugely important to us, was our weekly ops reviews. And actually lots of teams in HubSpot do this, where every week we'll all sit down and we'll say, okay, what alerts did we see in production and in QA during the week? What exceptions are being logged? And let's completely commit to fixing everything before next week. And that's kind of painful. And, you know, throughout last year, sometimes we were like, all we seem to be doing is like fixing bugs and improving reliability, but it actually was hugely necessary. And finally, metrics. So when you send a lot of data, you know, any kind of textual log file is just not going to work for you. You need to look at things in aggregate. You need to look at percentiles. So we have some, you know, obvious things, like we look at how many emails we're sending per minute and what effect that has on, you know, CPU and memory usage. We measure very precisely the time it takes to deliver messages. Again, we're looking at percentiles. What's the median, the 95th and 99th? A lot of problems can kind of hide in the 99th, and unless you address them, they'll start to shift down to a greater proportion of emails. And then we have some more like weird specific ones, right? So we have a metric and alert that will tell us how many weeks before we have to buy more IP addresses from Amazon, right? Because we don't want to run out of those. And then we've got even more specific stuff. So this graph is the 99th sending time, but just for dedicated accounts and just for emails that took more than 1 minute to deliver. And like each one of those colors represents a different reason for the delay. So I think the purple is like retries, the blue kind of one above it is queuing, and then the kind of pinkish one, I guess, was deliberate concurrency limits that we put on our system to stop it overloading. And you know, not overloading is kind of a big deal as well, right? So as we're kind of turning up the volume and expecting to get more traffic, we need to make sure we don't just, you know, just get more than we can handle and die. And the problem about email in particular is that volume is like really uneven. People don't just send, you know, 1 email per second for a long time. In particularly Tuesday at 11 a.m. precisely at EST, there was a blog post on HubSpot.com saying, you know, we've combed through all the data. We've figured out if you really want your emails to be opened, you got to send it on Tuesday, and it should be at 11 a.m. EST, which is like great for marketers, terrible for engineers. So like we have this very bursty traffic, right, where the system is quiet at some points, really, really busy at other times. We also have, you know, individual emails can take very different amounts of time because we're talking maybe to Gmail, they're super fast, or maybe to some, you know, server different side of the world, they're much slower. I know the general strategy was like, okay, async everything. So by using completable futures everywhere, We have async SMTP and DNS. We call HBase async. All our Kafka workers are async. And this allows us to handle much larger amounts of concurrency than we would if we just had to dedicate a thread to everything. And it also means that, slow things like sending slow emails doesn't slow down other faster emails. And so we can do things at very different rates. The problem with making everything as async is that you very quickly run out of memory unless you deliberately slow yourself down. So the reason for this is we have like these async Kafka workers, and they'll basically tell Kafka, just give me some more emails, give me some more emails. And, they get put off into a queue. Kafka is so fast and has so much data that it can very quickly swamp your service. So what we had to start doing is introducing rate limiting, like throughout the whole system. To avoid those out of memory errors on our Kafka workers, we have like concurrency limits where we'll actually count the number of emails that we have at any one time. We also work out the size of those emails to make sure that, a big influx of larger emails doesn't kill the system. We also do distributed rate limiting, which is kind of a harder problem, but an interesting one, so that our distributed systems won't overload one target system, which is bound to a sending IP. So that's another problem. So we introduced a bunch of rate limits in different parts of the system to make sure we didn't overload with all this extra volume. And then we had like another problem, which is, okay, we have like a big backlog of traffic here, and we're not sending the emails. What's going wrong? And so we turned to another metric, right? So now we have another metric, which is like, which of our rate limits are active at any one time? And that turned out that was really important. So that was actually able to say, okay, do you know what? The memory that we have on some of our workers is just too low, and that's actually causing us to go slower. So it's pretty easy, and we can use our platform to say, just give everything twice as much memory, and it works. It's still, so it works well, and it's kind of tuned, but I think we have room for improvement. In particularly the rate limits, we're going to do some work this year on learning those better, making it more adaptive to different kinds of load that we have. But generally the system is actually working really well. So if we look at 2017, we got two. You definitely can't read the legend here, but the red graph is volume, right? So it's like hundreds of thousands on the left-hand side, and the peak there is like 25 million. And then the green one is alerts, right? And actually, I just didn't have data for the start of the year. But you can see at the start, like with not so much volume, comparatively speaking, we had a ton of alerts. We worked really, really hard to make the system more mature. And as we go throughout the year, there's a few spikes, but generally things have been a lot more reliable. And particularly at the end of the year, we did pretty well. It's also worth noticing that the points where like we have very few alerts was where we just stopped deploying stuff. Turns out that's pretty useful. So you can see like when I went on holiday and that this was like inbound week where we have a big conference, and then this was the end of the year. So to recap, adding virtual hardware is like really easy. If all you had to do was to scale was like, hey, let's add some more CPU, let's add some more RAM, that would be super easy. But we found doing things like using feature switches to introduce changes, deploying frequently, just iterating and paying really attention to what's going wrong. Load tests and metrics will find bugs before customers do. So a lot of those alerts were actually, internal alerts that told us there was a problem, but customers weren't affected. And that's it. Thank you. Any questions? Hey, Mike.
I just wanted to ask, have you considered using any streams? I'm not sure what's Java, but Akka stream is probably available for Java, because this rate limiting is like perfect case for back pressure. Yeah. So you create like source back pressure, and you don't need rate limiting. Like it will be executed at the limits that it could be executed.
Yeah, so that's a great question, and back pressure is one of the things that we are like planning to implement. Our problem is really rate limiting between different like servers that are that have different data sources. So we're using Kafka, it's going to come just as fast as possible. There's no back pressure for Kafka, right? Unless you just stop processing messages, which is exactly what we do. And then we have this quite specific kind of rate limiting that we need to do, where we have like n workers, which are all funneling data towards one particular instance, which is bound to an IP that AWS is being told to send email from. And so that's kind of a more complicated problem. Maybe it's possible to use Akka to do that. I don't know enough about it.
I believe the rate limiting already implemented there. Like if your source implements back pressure, so if you could stop reading some stuff, then rate limiting is, I believe, standard. It's already there.
So we use gRPC, which has some support for back pressure, but it's a case of figuring out how to do it fairly as well, right? So we don't want to have some workers experience all the back pressure, other ones not, and then we get some emails delivered faster than others, maybe in an unfair way to our customers and so on. So, but definitely it's something we're looking at, yeah.
Thank you.
How do you know if some mail server is not throttling you? So it's not blocking you or slowing you down. Do they give you a metric to do that, or like?
How do we know if they're throttling us?
Yeah.
So I guess there's a bunch of different ways they might be throttling us. One is some mail servers will allow you to open as many concurrent connections as possible. Again, Google are the prototypical example. Others will say, nope, from this IP, you can only open 2 connections or 1 connection. So that's one form of throttling. And we kind of slowly try and increase the number of connections as volume increases, but we need to kind of respond to those messages and then, not annoy them, essentially. So that's one thing. And they also will write back a bit of text, and we have to just parse the text. And so, we've spent some time kind of looking at the text that email servers give us, trying to figure out and classify those things, and in some cases extract a number from that we can use to decide when to send again.
Hey, so how do you deal with 1, people trying to use your system to send spam, and 2, if they do send spam, getting off blacklists?
So we put a huge amount of effort into that, as you can imagine. So 2 of those 6 teams basically are devoted to that problem. We're an inbound marketing company, and we have, not only do we kind of, preach inbound, it's really important to us, but also we really believe that if you want to get clicks and engagement through your email, you need to send to people who really want to receive those emails. So we have a bunch of things, built into the product, like we'll automatically not send emails to people who aren't interacting with them. That actually does a lot of work to help that. We also have systems which will, notice that an individual email doesn't seem to be performing well, and we'll stop sending that, and a bunch of other things. And we have more than we could possibly go into at the moment, but essentially it's a huge part of what we do, figuring out how to protect that IP reputation and help our customers, send better email.
Hi. With all the recent attention on machine learning and support vector machines that's going on in the industry right now, have you guys considered using those for handling your rate limiting and shaping your traffic better?
I don't think we're using, or we've considered using those for rate limiting. It would be interesting to chat to you about that, but we are using some ML at different parts of the sending pipeline, yeah.
Can you offer a bit more detail about how you use HBase for locking?
Yeah, sure. So HBase has some small level of support for atomic operations. In particular, it has this check and put. So we can basically say, hey, it's a bit like if you've used an atomic integer or something in Java, you can say, hey, set this value to 1 if it's currently 0. And so one thread that has an email can say, hey, set this lock timestamp to the current timestamp, provided there isn't currently a lock. And if we get back, yep, we managed to set that, then we have the lock. And also, we want to automatically expire those locks. So another condition that we can write is if either there is no lock, or if the lock is 30 minutes old, then you can acquire the lock. And we use that kind of system. Anything else? Okay, thanks everyone.
Well, thank you everyone for coming to our event. We're gonna go back in the kitchen area behind you and chat and mingle if you want. Thanks again and have a good evening.